Hi, we're going to solve this truss for POE, Project Lead the Way, Principles of Engineering. We're going to go through the steps to doing a truss analysis problem. And so here's a truss that we've been given. We've got joints at A, B, C, D. We've got a pin support at A, a roller support at C. We have a load of 50 newtons at joint D. We've got some lengths. We've got this length here from A to D is 7 units, from D to C is 3, as well as height of 3. Obviously not drawn to scale, but we're going to go with the data that's been given. First, you want to make sure that the truss is statically determinate, meaning we can solve it. The formula for statically determinate is 2 times the number of joints should equal, this is really a question mark, to determine is it statically determinate. We're kind of asking ourselves, will this be true? M is the number of members, and R is the number of reaction forces. So the number of joints was 4, A, B, C, and D. So we've got 2 times 4. Again, still a question mark really, is it equal? The number of members, well, from A to B is 1, B to C is 2, C to D is 3, D to A is 4, and then we have B to D is 5. So we had 5 members. The number of reaction forces should be 3. A pin support produces a reaction in the Y direction and the X direction. So we've got 2 there. A roller support can only produce a reaction perpendicular to the load there. So it's just as we're, the truss is pushing down, it can push back up, but it can't provide any reaction force horizontally because it would just roll. Okay, so we have 1, 2, 3, and we end up with 8 is equal to 8, so it checks. It is statically determinate. Okay, we are going to want to find the angle measures in here. We can't assume that at angle B here, ABC, is a 90-degree angle. Some students are tempted to call that a 90. And if they do that, after finding angle A, they'll think that A and C are complementary, and they're not. So how we're going to find these angle measures, I'm going to find A and C, is we're going to go ahead and use lengths. I'll go ahead and write 3 here. We're going to use lengths, and after that, we won't really have, we'll have a little bit of a need for a length down here, but mostly we'll be working with forces from that on. Alright, so we're going to use a little right triangle trig to find angle A. If you focus in on the truss where you've got 7 and 3 lengths in angle A, in a right triangle here you have the opposite and the adjacent. And we have a tangent ratio that says the tangent of angle A is equal to the opposite over the adjacent. This is using SOHCAHTOA. And when the angle is the unknown, you get rid of the tangent by taking the inverse tangent. So we're going to have the inverse tangent of A, and that gets us just A. And if I take the inverse tangent on one side of the equal sign, I have to take the inverse tangent on the other side as well. So that's what I'm going to type in my calculator. And I've got one here. I'm going to hit the inverse tangent of 3/7. And make sure your calculator is in degrees. I get 23. I'm going to round to just 1 decimal place, so 23.2 degrees. And I'll fill that in here, 23.2. We're going to repeat the same thing over here for angle C. So at C we have 3 and 3. Again, not really drawn to scale, but there you go. So I'm going to write an equation here again. Opposite and adjacent is tangent, so the tangent of angle C is 3/3, which is 1. So I will have the inverse tangent of the tangent of C is equal to the inverse tangent of 1, or 3/3. And so those cancel each other out, leaving the angle C. So what is the inverse tangent of 1? And it's 45 degrees. Okay, you might have known that because you have an isosceles right triangle. So if those two legs are congruent, these two angles had to be congruent. Knowing that's 90, that would have to be 45. But you might not have a problem like that, so just make sure you know how to use SOHCAHTOA, set up a trig ratio, and solve for the angle. Okay, before we move on, I'm going to go ahead and ask that you draw a free body diagram. Really, you're going to draw this truss, but we're going to get rid of the lengths right now, and instead of drawing the full member, I'm basically going to leave a gap here. Okay, so I'm going to just kind of start framing out like here's A. Okay, and let's say that D is right here. So at D, okay, and this would intersect kind of right up here. So I'll have that come down and that. And then right here, so that's A, that's B, that's C, and that's D. I got member BC. Okay, and now I'm going to go ahead and put in my reaction forces and label them. So because that's a pin support, I have a reaction force at A. So I'm going to put R for reaction force, subscript A, and then a subscript Y as well. So reaction force at A in the Y direction. I also have the horizontal reaction force because of that pin support. So we're going to call that one reaction force at A in the X direction. Over here at C, we have a reaction force only in the Y direction. So reaction force at C in the Y direction. And then we have our load. And for this problem, we told you it was at D and it was 50 newtons. And we'll fill in our angle measures here as well of 23.2 and 45 degrees. Okay. Now, before we begin finding the forces of the internal members, we need to look at the external forces. So that's just keeping the truss, keeping the whole body as one unit, and making sure that this truss is not moving up and down, it's not moving right and left, and it's also not spinning. The pin support is where maybe it could spin. That's the one point that's really stuck. Well, statically, this truss should be in static equilibrium, so meaning it's not moving. So we need to make sure that anything that would cause it to rotate, any forces that would cause a rotational, a moment we call it, effect, that they are balancing each other out and they net zero. Any force that's away from this pin support, this is acting as a fulcrum, as a lever, would create a rotational effect or a moment. So like this load, this 50 newtons down at D, that would make this truss want to rotate down. Okay? So there's got to be something that's stopping the truss from rotating down. Do you see it? It's the reaction force at C from the roller support. So as the load is pulling it down, that reaction force is pushing back up. That force would actually want to make it go that way. They're balanced. So we are going to use all three static equilibrium equations right now to look at the entire truss body and say that it's not rotating, it's not moving up and down, it's not moving left and right. So we're going to first start with the moments. We're going to say the sum of the moments is 0, and then you list out what are those moments. Well, we have the, I'll put F force at D. I don't know, this is kind of, I'm just making this up really. There's a force at D and it's a load, right? So there's that, and it has a distance. Remember, moments, maybe a helpful little thing is that a moment is a force times a distance from the fulcrum. And so we've got that force times a distance, which was 7, plus the reaction force at C in the Y direction times a distance, and that from the fulcrum right here was 10. And these need to add up to equal 0. Now we can go back and fill in some other things. You do need to realize for a moment too that counterclockwise is a positive moment, and clockwise is a negative moment. So this force, this loaded force here, would be wanting to make our truss rotate clockwise, which is negative. So I'm going to come in here and put negative 50 times 7. My reaction force is unknown, but it would make it go counterclockwise, which is positive, so it'll stay plus. And there you go. So just to recap, right now the equation we're writing is simply saying that the sum of all the moments has to become 0, has to add up to equal 0. I have two forces that are creating moments, the load and the reaction at C in the y direction. So these need to add to make 0. One's in the negative direction, one's in the positive. So the good news is there's an unknown. So this equation, this relationship, is going to help me find something that I didn't know. Good news for you is to have only one unknown. If you have more than one unknown in an equation, then you're going to need to go find another equation to start with. Okay, so let's start solving this algebraically. This is negative 350 plus the reaction force at Cy times 10. So algebra, you're going to add 350 to both sides, and then you're going to divide both sides by 10. And dividing 350 by 10 is 35. So we get 35 newtons. For that reaction force. And as I solve here, I'm going to come and in a different color, I'm going to update my free body diagram with information that I've found. So this is now 35 newtons, that reaction force. Okay? So that's one of our three static equilibrium equations. The next one is going to say that the sum of all the forces in the y direction have to add up to equal 0. All right? So anything vertical acting on the truss, the whole truss. Well, there are three. I have a reaction force at A in the y direction. That's pushing the truss up. I have the load is pushing down. And then I have this reaction force is pushing up. So anything that's vertical. All right, so I'm going to list those out. I have the reaction force at A in the y direction. I have the load, so just the 50. I have the reaction force at C in the y direction, and that's it. And they all have to add up to equal 0. Now, you also need to know that with vectors, anything going up is positive, going down is going to be negative, going to the right is going to be positive, and left is negative. So right now, the reaction force at A in the y direction, that's up, that should be positive. The reaction force at C in the y direction, that's going up, should be positive. This 50 is down, it should be negative, so I'm going to put a negative 50 there. All right. Now, this one we've actually solved. Our moments, the sum of our moments becoming 0, told us that that had to be 35. So in the next step, I can come in here and I can replace the reaction force at Cy. Instead of it being an unknown, I can replace it with the number 35. And do a little simplifying algebra. These become negative 15, add 15 to both sides, and we find out that the reaction force at A in the y direction is 15. And that would be newtons again. So let's update that. So this is 15 newtons. Okay, the last static equilibrium equation is going to say that the sum of all the forces in the x direction, so now we're talking horizontal, are going to add up to equal 0. Well, there's only one. So there's nothing else to even balance with it, possibly, so the reaction force at A in the x direction plus nothing else has to add up to equal 0. So that's easy, it's just 0. So we'll put that there. Okay, so we've got our free body diagram. We know what all of our reaction forces are. And we are ready to move on and define these 5 members, the internal forces. Okay, and how we do that is we use a method called the method of joints. And here are some things that you need to keep in mind. Okay, For internal forces, we're going to use a method of joints, which means we look at two static equilibrium equations at each joint. We don't deal with the moments anymore, just the sum of the forces in the y direction and the x direction. So these two relationships we'll be going and using at each joint. We are going to assume that members are in tension. Tension means that the member is pulling on those joints at either end. So the arrows are going to go away from the joint. We're going to assume that. It might not be correct, but we'll assume it. Okay. After making that assumption, keep in mind what directions are plus and positive and negative. Okay. So positive directions are up and right. Negative directions are down and left. After solving, if we get a positive value, that means that our assumption that the member was in tension was correct. If we get a negative, that means our assumption was incorrect, and the arrow actually was not going away from the joint but coming back to it, and that member must be in compression. As we solve, we will update our free body diagram up above as we go. Okay, or even other little pictures that we've used. So the first joint we are going to analyze is joint A. Joint A is a pretty good one because I have a reaction force in the y direction and a reaction force in the x direction that are both known. Okay, so I'm going to draw this free body diagram, just that joint alone. So we've got a member AB. We have a member at A going to D. We have a reaction force that's known to be 15. And we have a horizontal reaction force known to be 0. Okay, so if you want to label those, you can. The reaction force at A in the y direction, and this is the reaction force at A in the x direction. Okay, so we're going to start by using this relationship that says I'll zoom in a little bit here. We're going to start by saying that the sum of all the forces in the y direction have to add up to equal 0. So you have to be able to look at this and find all the forces in the y direction. Okay. I see one vector that's vertical, and that's it. That's vertical. However, there's a diagonal one. And the one that's diagonal, well, if it's pulling up and right, notice what I said, it's pulling up and right. Vectors, remember, have component vectors that make it up. So we can go in and we can say this member AB, since it'd be pulling up and right, part of it, okay, I'll call ABX, will be a horizontal component to that. But then there'll also be a vertical component, so I'll call this ABY, that's pulling vertically. And so we basically are replacing member AB, which is a resultant vector, with two component vectors now. So that instead of dealing with this diagonal, we'll deal with only a vertical or a horizontal. So now when I look at the sum of the forces in the y direction, there's two. I have the reaction force at A in the y direction, and I have the the y component, the vertical component of member AB. So I'm going to call that AB sub y. And those have to add up to equal 0. All right, so we can now fill in what we know, which is that the reaction force was 15. That 15 is up, which is a positive direction. We are going to assume, okay, that this was in tension. So we've got our arrows pointing up and right. And we solve. And after solving here, subtracting 15 from both sides, we get a negative 15. And the negative tells me that that arrow was not actually going up. It was going down. So if I redraw, and I'm going to want to redraw this anyway, I'm going to redraw ABY. okay, real quick, and that was really down. And so this vector AB, the arrow's got to be on one end or the other. If this is down, then the arrow really should be here, and that means that it was down and left, not up and right. So we can redraw our free body diagram, our component forces, and so this is AB, and this is ABX, and this is ABY. And ABY, we just found out, was negative 15, right? So this is negative 15. All right. Now remember, up above we had found these angle measures. I know that at angle A, this is 23.2 degrees. So now comes the point where we need that. So this 23.2 degrees, okay, is also this angle right here. So in geometry, you may remember that alternate interior angles are congruent. These horizontal lines, AD and ABX, would be parallel. And so I really know that that's also 23.2. Okay, and so what I now find myself with is a right triangle. All right, horizontal and vertical are going to make a right angle, where I know an angle and I know one side. And if I have an angle and a side of a right triangle, I can use SOHCAHTOA, right? Sine, cosine, or tangent. And I'm going to find both of these two missing sides. AB is a member, so that's obviously one that I really want, but you'll see that I need ABX here in a second. Okay, so with respect to that angle, this is the opposite leg, and this is the hypotenuse. So opposite and hypotenuse is sine. I can write a trig equation that says the sine of 23.2 degrees is equal to the opposite, negative 15, over the hypotenuse, AB. And then I'm going to solve that. I'm going to skip some of those algebraic steps, but you know, I'd multiply both sides by AB to get the AB out of the denominator. I would divide both sides by the sine of 23.2, that's a decimal point, to get the AB alone. So in the end, I end up with negative 15 divided by the sine of 23.2. You can see I'm typing on my calculator here. And I get, okay, negative 38, I'm going to round to the nearest tenth, 0.1. So negative 38.1. And the negative is, again, telling me that this was in compression, which I kind of already knew. So that negative, though, that tells me compression. All right, so we just found our first member. So I'm going to come up here, and I don't actually put a negative now. I'm going to go ahead and put 38.1, and then in parentheses, I'm just going to put a C to let me know that that's compression. So that means that I would know that the arrow, if I were to draw this free body diagram, is actually, you know, going this way, coming back towards the joint, and that means at B it would be going towards B as well. Okay, it's pushing out. Okay, now I'm going to do the same thing to find ABX, but just to make sure you understand why, look, the next thing I would do is, instead of saying the sum of the forces in the y direction is 0, I'd say the sum of the forces in the x direction have to be 0. And when I look for all the forces in the x direction, there are 3. There's the reaction force at A in the x direction. There is member AD. And this diagonal one had a vertical and a horizontal, so there's ABX. And at the moment, I really only know the reaction force is 0. I don't know AD. I want to find it, but I don't know it. And I haven't found ABX, but right here I see that I can find it. So if I can use you know, a trig equation to find ABX, I'll only have one unknown, and then I can find AD. Okay, so let's go right back to here. ABX, that is the adjacent leg to this angle, adjacent. This is the opposite. Opposite and adjacent is tangent. So you can use the tangent of 23.2 degrees is equal to the opposite over the adjacent, which is ABX, I don't know if my screen went out there on you for a second. And then I'm going to, again, just kind of do a little bit of algebra, multiply both sides by the ABX, so it's out of the denominator. Okay, divide both sides by the tangent of 23.2. And so what I end up with is negative 15 divided by the tangent of 23.2. Sorry, I moved my mouse into place that my screen's getting covered. Okay, so negative 15 divided by that, and I get negative 34.99. So basically negative 35, right? Now, what I encourage you, if you are a little weak in your algebra skills and you need to show that, just so that later you come back and you're wondering, I do have students that aren't exactly perfectly clear and confident on how to go from here to here. And so write out those couple steps algebraically of what you're doing to manipulate this equation. Okay, so ABX is now known to be negative 35. So I plug that in for the sum of my forces in the x direction, and AD is the only unknown. So I'm going to add 35 to both sides, and I've got AD. And AD worked out to be positive, and so positive means that it is in tension. Okay, so again, let's update our free body diagram. So AD right here is 35 newtons. And I'll put a T for tension. Okay, so we have finished solving at joint A, and we're now going to move on to another joint. So the next joint I'm going to move to is D. Okay, if you look up here, if I slide over, now that I found this, D is a good one because I have one horizontal and one vertical. I have the load, and there's only 4 vectors here. There's no diagonals to do any component forces. So I've got one horizontal and one unknown, so I should be pretty fast at getting CD. I've got one vertical and one vertical member unknown, so again, I should be able to get those really quick. All right, so let's just draw what we have though. We've got at D here, we have CD is unknown. We assume it's in tension. We have AD known to be in tension. We have our load going down, and we have BD, we don't know, assuming tension. Okay, so fill in the numbers you know. We know that this is a load of 50. We know that this AD was 35 newtons, and we do know the direction there. So when we say that the sum of the forces in the y direction is 0, well, that's the load of 50, and because it's down, that's a negative direction, so we're going to have a negative 50 because of the direction down, plus BD, okay, not really the vertical component, it is vertical itself, so those have to make 0. So not hard math here, just add 50 to both sides and you find out that member BD is 50 newtons, and that's positive, so that's tension. All right, so there you go, that's another member. So this is 50 right here. And do the same thing in the horizontal direction. The sum of the forces in the x direction have to add up to equal 0. Well, I have AD plus CD have to make 0. AD I know is going to the left, so I know that's negative. CD I don't know, so this is going to be a negative 35 plus CD is 0. Add 35 to both sides and you get 35 newtons. Again, positive means tension. So let's go update our free body diagram at the top. That should be the fun thing, getting to fill these in. So this is 50, it was a positive 50, so that means T for tension. This was 35 newtons, so that's again positive T for tension. And we have 4 out of the 5 members. The only one we're missing is BC. BC is going to be solved for either using joint B or joint C, and it doesn't really matter which one. You really have 3 different kind of vectors here. Now that's a diagonal, and that's a diagonal. 2 of them are diagonal, so that might get a little more complicated than here, where I only have 1 diagonal, 1 vertical and 1 horizontal. So if you think of, when you've got these diagonals needing to work with component forces. So I think this one's probably a little easier since I have only 1 diagonal. So let's go ahead and draw this free body diagram, kind of remind ourselves of the numbers down below in our picture, and we will find BC. And we're about done. So that free body diagram looks like this. We have BC unsolved for, so we're going to assume tension, assume it's going away. We have CD. Okay, this is joint D. Make sure we know that. And we have this reaction force we know is pushing up. That was 35 newtons. So we'll call that's the reaction force at C in the y direction. This right here was CD. We know that's tension. All right. And we know this angle measure was 45 degrees. It really doesn't matter if you use the sum of the forces in the y or the x direction. You will only need one. But let's go ahead and write out that the sum of the forces in the y direction is 0, and just kind of see what happens. So vertically speaking, we'll have this reaction force at C in the y direction. And then, do you see any other horizontal forces? Not explicitly, but we've got this diagonal one. So you again have since you have a diagonal vector, remember, you've got a vertical component in there. And so let's label that BC in the y direction, the y component. So we've got, remember, BC's y component, and that's it. Those are your 2 verticals. They need to add to make 0. Plug in what you know. We know that this one is 35, right? So if you subtract 35, you know that that vertical component is negative 35. Now, we're really close. If you found out that that is negative 35, okay, and you know this angle is 45 degrees, can't we just come back and use our right triangle? So let me just redraw just the triangle, right? You know that this is negative 35. You know both of these angles are 45 degree angles, and what we're looking for is BC, the hypotenuse. So you can write a trig ratio. Okay, looks like we've got an opposite and a hypotenuse, so that sounds like sine. So the sine of 45 degrees is equal to the opposite, negative 35, over the hypotenuse, BC. Do a little bit of algebra. You're going to multiply both sides by BC. You're going to divide both sides by the sine of 45. So you'll end up with BC is equal to negative 35, okay, divided by the sine of 45. And I've got, if I round that up, negative 49.5. And that negative means that it was in compression. All right, so that's the fun one to fill in, 49.5, because it is the last one. That truss has been solved. Okay, so we can see as we put a load at D, we're getting that this vertical member is under tension. It's getting pulled. These supports aren't moving, right? So these are getting pulled. These are in tension. And as that happens, you know, think of if B were to move just slightly down, it's really like B is getting closer to A and closer to C, and that's why these members are really in compression. Okay. So instead of those members getting pulled, they're getting compressed. All right, well, that is how to do a truss analysis. Worked out pretty slowly, so I hope that helps, just to go through it nice and slow, take our time, and I hope you have some success solving truss problems in your POE class. Thanks for watching.